Let's continue with the exercise. Question number 5. On all real numbers, relation R is defined in this way. A related to B if A is less than or equal to B cube. Question is check for reflexive, symmetric and transitive properties. So here, first property, reflexive. So here it is on R. So if I try for fractional values, if I take 1 by 2 and 1 by 2 with itself, so here 1 by 2 and 1 by 2 whole cube, which is 1 upon 8. Now you know that 1 by 2 is not less than or equal to 1 upon 8 because this is smaller than this. So you can say that 1 by 2 is not related to 1 by 2. Even if you try 1 by 3, again it's not related to 1 by 3. Why? Because 1 by 3 is not less than or equal to 1 by 3 the whole cube, which is 1 upon 27, and so on. So you can say that R is not reflexive. One example is sufficient here, but I have given two. Even if you recall, this is just for your information. If I take 2, obviously 2 is related to 2. Why? Because 2 is less than or equal to 2 cube, which is 8. If I take 3, obviously 3 related to 3 because 3 is less than or equal to 3 cube, which is 27. But such examples are not important in this case. For fractional value doesn't hold, therefore it cannot be reflexive. Second property, symmetric or not. So if I take here for example 1 and 2, so let's try for this. 1 is less than or equal to 2 cube, you know this is true, so 1 related to 2. Now you reverse, is 2 related to 1? That's the question. So check whether 2 is less than or equal to 1 cube, which is 1 or not. You know that 2 is not less than or equal to 1, so 2 is not related to 1. So immediately you can say that R is not symmetric. You may have some example for which reverse might be present, but this is one example for which reverse ordered pair is not present, therefore it's not symmetric. Now we go to third property, transitive or not. Now, this is very important case. You can find trial and error some examples for which the relation is not true. So I'll show that this is not transitive by taking one example. If I take 16 and 3, 16 related to 3. Why? Because 16 is less than or equal to 27 3 cube, as 16 is less than or equal to 3 cube, which is 27. Now if I take 3 related to 2.5, you can verify. Reason is 3 is less than or equal to 2.5 the whole cube, which is 15.625 roughly. But if I take now in transitive property, you check this for this. So here if I take 16, this element, and this one 16 and 2.5 the whole cube, which is 15.625. so you know that this is not less than or equal to this. So you can say that 16 is not related to 2.5. So from this example you can say that it's not transitive again. Not transitive. This is just one example I have given. You can find many such examples. Only one example is sufficient. A related to B, B related to C, but A is not related to C, therefore it is not transitive. So question number 7 here. definition of the relation R is this: x related to y if x and y have the same number of pages, where x and y are books in the library. So first one is reflexive property here. So for reflexive property you need to take member with itself. So clearly x and x have same number of pages, so x related to x. Reason is this: for every x you can write. Both are identical books here, so of course they have the same number of pages. So you can say that here R is reflexive. R is reflexive relation. Now second property, which is symmetric. So what you need to do in symmetric, you start with suppose x related to y, and at the end check whether y related to x or not. This is what you need to do. So I'll start with this: suppose x related to y. So you can say that x and y, these are the two books, have same number of pages, This is by definition given to you. This is your supposition. Now you want to show that whether y related to x or not. So can you say that y and x also have the same number of pages? Of course, you are just going to change the order here. If x and y have the same number of pages, y and x also have same number of pages here, same number of pages. So you can say that as per definition y related to x. So therefore whenever x related to y, it implies y related to x for every x and y. So therefore here R is symmetric. So for transitive property, you start with this two: x related to y, y related to z, and check whether x related to z or not. So we start with this two. So suppose x related to y and y related to z. Now what is the meaning of x related to y? X and y have same number of pages, What is the meaning of y related to z? Y and z have same number of pages. X and y have same number of pages, y and z have same number of pages. Here suppose 25. So this is also 25, then z must have 25 pages. So from these two you can say that x and z, these two books, must have same number of pages, If x and y, two books, have same number of pages, here y is common, remember. Y and z also have the same number of pages. Suppose x has 100 pages, y has 100 pages, y has 100 pages, then z must have 100 pages. It means x and z must have the 100 pages. So therefore x and z have the same number of pages. So therefore by definition you can say that x related to z. So what you have concluded, whenever x related to y, y related to z, it implies x related to z for every x, y, z here. So therefore R is transitive relation. So R is reflexive, symmetric and transitive, therefore R is an equivalence relation. R is an equivalence relation. Equivalence means reflexive, symmetric and transitive. Next question, question number 8 here. Your relation is defined on A equals to this set 1, 2, 3, 4 and 5. Set consisting of just 5 members. Definition of the relation R is this: A comma B such that modulus of A minus B is even. This is definition. Like you can say, for example, 1 related to 1, because 1 minus 1 is 0 and it's even. You can say 2 related to 2, because 2 minus 2 is 0 is even, and so on. So here the first task is we show that it's an equivalence relation. We show R is an equivalence relation. Means we need to show that it's a reflexive, symmetric and transitive. R is an equivalence relation. So if you want, you can list out the members of the relation set here also, because there is a finite set. So here, that's one way. So let me write R as a, for example, set of ordered pairs. So here 1 1, 2 2, 3 3, 4 4 and 5 5 will be there. Why each of this will be present? 1 minus 1 0, which is even, 2 minus 2 0, which is even, 3 minus 3 0, which is even, and so on. So from this clearly you can say that it is reflexive. Now the other ordered pairs, you cannot take 1 comma 2 because its difference is odd. Can we take 1 comma 3? Yes, because 1 minus 3 is minus 2, and if we take modulus it's 2 and it's even. So 1 3 will be there. 1 4, no. 1 5, yes. 1 5 is there. Now go to 2 1, no. 2 2 already chosen. 2 3, no. 2 4, yes. 2 4. Why this? Because 2 minus 4 is minus 2 and it's an even. 2 5, no. Go to 3. 3 1, yes, because 3 minus 1 is 2. 3 2, no. 3 3, yes. Can we take 3 4? No. 3 5, yes, because difference is 2. Let's go to 4. Can we take 4 1? No, difference is 3. Can we take 4 2? Yes, so here 4 2. Can we take 4 3? No, because there the difference is 1. Can we take 4 4, which already taken? 4 5? No. Okay, so we go to 5 now. Repeat. 4 4 1? No. 4 2, yes. 4 3, no. 4 4 already taken. 4 5, no. Similarly 5 1, yes, because difference is 4. Can we take 5 2? No, difference is 3. Can we take 5 3? Yes, difference is 2. 5 minus 2 is 3, no. 5 3 2. 5 4, no. 5 5, which already taken. So this many ordered pairs will be there. This is a finite set, so we can list out this. Now from this you can see very easily 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5 all are present. So this is reflexive. 1 3 is present, 3 1 is present. 1 5, 5 1, 2 4, 4 2 is not there. Yes, 4 2, 3 5, 5 3. So reverse is also present. So this is symmetric. So here R is reflexive. Reason is 1 related to 1, 2 related to 2, and so on. R is symmetric also, because you can see that 1 related to 5, it implies 5 related to 1 is also there. 2 related to 4, it implies 4 related to 2 is also there. 3 related to 1 implies 1 related to 3 is also there. So because of this it is symmetric. Third property, it is transitive also. Why? Because you take two ordered pairs. Suppose I have taken 1 comma 5, which is in R. Now you take any other ordered pair having 5 at the first place. Suppose I have taken 5 comma 1 is also in R. Now check whether 1 1 is in R or not. It is there. So 1 comma 1 is in R. How do I write in another language? 1 related to 5, 5 related to 1, it implies 1 related to 1. If you take one more example here, if you want, suppose 2 related to 4. Now you get one ordered pair having 4 at the first place. Suppose I have taken this one, 4 related to 4. Now drop this common one, take this 2. Can you say that 2 related to 4? Yes, this is the first ordered pair itself. So here also it is true. Now for any other ordered pair, suppose I have taken 5 related to 3. You can take 3 related to 1, for example. Now check for 5 related to 1 is true or not. 5 related to 1, is this true? Yes, 5 comma 1 is there. So therefore R is transitive. You can give some more if you want. So here R is an equivalence relation. R is a equivalence relation. It's reflexive, symmetric and transitive. Further you are asked, this is one part which is over. Further you are asked, show that 1, 3 and 5 are related to each other. What's the reason? Here reason is related means difference of any two should be even number. So here if you take 1 and 3, they are related. If you take 3 and 5, they are related. If you take 1 and 5, they are related. Because here every time difference between these two is an even number. So here members are related to each other. Members are related to each other. Same way, one more set you are given, 2, 4. So here also as 2 related to 4, difference is 2, even 4 is also related to 2. So therefore these members are related to each other. Members are related internally. But one more thing you are asked, no element of this is related to this. Why? Because you take any member from this and one member from this, you will notice that the difference is not an even number. Suppose I have taken 1 and 2, so difference is 1, which is not even. Suppose I have taken 5 and 4, difference is 1, which is not again in even. So therefore no member of this is related to any member of this set 2, 4. Now here if I take one member from here, for example 1, and one from here, so 1 is not related to 2. Why? Because 1 minus 2 is not even. Suppose I have taken 3 from here and 4 from here, 3 is not related to 4 because 3 minus 4 is not an even. If I take 1 from here, suppose 5, and 2 from there, again not related because 5 minus 2 is not an even, and so on. So therefore you can say that no element of 1, 3, 5 is related to any element of 2, 4, and therefore next question. There you are given set A equals to all x from z from 0 to 12, that is this 13 integers starting from 0, 1, 2 up to 12. This is set A. First you can try, this is for you. Second, here relation R equals to A comma B such that A equals to B, that is numbers should be equal. So here you have just 13 members on a set, so you can list out if you want. So R equals to here 0 equals to 0, so 0 comma 0, 1 comma 1, 2 comma 2, and so on up to 12 comma 12. Only this many members will be there. You cannot have 1 comma 2 because 1 is not equals to 2. You cannot have 2 comma 3 because 2 is not equals to 3. Numbers should be equal. This is the relation set. Now we want to show that this is an equivalence relation. So we show that R is equivalence. R is an equivalence relation. So we need to show that it's a reflexive, symmetric, and transitive. So first property, reflexive, which is very obvious. Reflexive. For every A, for every member of the set A is always related to A because A is equals to A. Right? Therefore, it is reflexive. Now, second one is symmetric. So you start with this. Suppose A related to B, and at the end you show that B related to A. Now if I start with suppose A related to B, it implies A equals to B. So it is same as B equals to A. So therefore you can say that B related to A. Even directly also from relation ordered pairs you can show that here 0 comma 0 reverses itself, 1 comma 1 reverses itself, 2 comma 2 reverses itself, 12 comma 12 reverses itself. So here I have given the general proof for every AB. You can say that whenever A related to B, it implies B related to A. For every AB this is true, and therefore it is symmetric. Now third property, which is transitive. So for transitive property, you know what's the method. Start with suppose A related to B and B related to C. This means A equals to B, and this means B equals to, now we need to show that A related to C in this case. So let's start with this two first. So suppose A related to B here and B related to C. What's the meaning of A related to B? A equals to B, B equals to C. This is given to us. So from this two you can say that A equals to C. So therefore A related to C. So you have shown that for every A, B, C, whenever A related to B, B related to C, it implies A related to C, and therefore R is transitive, and therefore R is an equivalence relation, because you have shown that R is reflexive, symmetric, and transitive. So it's an equivalence relation. Now further here one more question is, find all elements related to 1. This is the question. Find all elements related to 1. So obviously here there is only one element which is related to 1, that is itself, because 1 equals to 1. So all elements related to 1 is this one only, singleton 1, because here 1 related to 1. Even if you look at ordered pairs, you will realize because 1 equals to 1. So all elements related to 1 is just a singleton 1. Question number 10. Give an example of a relation. Your first question, which should be symmetric. That means the reverse ordered pair should be present, but it should not be reflexive, as well as it should not be transitive. You can construct any example of your choice. I'll try for first two. You will realize how to do, then you can do the remaining. So the relation should be symmetric, not reflexive, not transitive. Now when you take an example of a relation, you need to take a set. So let's take A equals to 1, 2, 3, 4. Randomly I'm taking one set. You can choose any set. Define a relation here. Relation R on A as. Now you want to form the symmetric relation. So I need to put 1, 1, 2, 2, 3, 3 and 4, 4. So now it becomes symmetric. Oh, sorry. I want symmetric. So reverse should be present. I'm sorry. I was thinking about reflexive. So here relation should not be reflexive. So all this should not be present. So just I'll take 1, 1 and 2, 2. I'll not take 3, 3 and 4, 4. So it's not reflexive. Now I'll put 1, 2. I want symmetric. So I need to put 2, 1. Suppose now next I'll take, let me take 2, 3. So I need to put 3, 2 because I want to make it symmetric. Now if you look at this 2, 1, 2 and 2, 3 both are present. So if 1, 3 is present, then it is transitive, but I don't want transitive. So I'll now close the relation. So this is one sufficient example for the given all three properties. Because of this 2 only present, it's not reflexive. 1, 2 is present, 2, 1 is also present. So this one, 2, 3 is present, 3, 2 is also present. So because of this you can say that it's symmetric, but not transitive. So because here 1 related to 2, 2 related to 3, but 1 related to 3 is not there. You can see that 1, 3 is not there. So therefore it's not transitive. Not transitive. Here 3 related to 3 is not there, 4 related to 4 is not there. So not reflexive. Not reflexive. And reverse are present. 1 related to 2 implies 2 related to 1. 2 related to 3, reverse 3 related to 2, which is there. 1 related to 1, reverse 1 related to 1. So because of all these, you can say that it is symmetric. So I hope this is clear to you what I'm trying to tell you. And this is not the only example. You can construct number of such relations. You know, relation is any subset of A cross A. Now A cross A would have 16 ordered pairs. So out of 16 you can form any. For example, instead of these I can take these also, remember. Or you can take these also. I'll not put 1, 1 and 2, 2 both, remember. I'll put just 1, 2 and 2, 1. So now for this relation again, you can see that it is not reflexive. Why? Because 1, 1, 2, 2, 3, 3 all are not there. It is symmetric because reverse is present, 1, 2, 2, 1. Even it's not transitive also because 1, 2 is present, 2, 1 is present, but 1, 1 is not present. So not transitive. So even this example will do. Any example of your choice you can construct. Next is you want transitive relation, but not reflexive, not symmetric. So I'll take a set for example. Again, let me take 1, 2 and 3 and define a relation. Define a relation R on A as R equals to, I don't want reflexive, so I'll not put 1, 1, 2, 2 and 3, 3. Not symmetric, that means reverse should not be present. So 1, 2 I'm for example putting. Next I have taken 2, 3. Now I want transitive, so I need to put 1, 3 also. Now you check for this. Here 1 related to 2, 2 related to 3, it implies 1 related to 3 is there. Now here your 2, 3, do you have any ordered pair having 3 at the first place? No. Here 1, 3, do you have 3 at the first place in this? No. So You can say that because of this it is transitive. This much you can notice now, it's transitive. Not a reflexive, which is obvious. Now you can answer it. Why not reflexive? 1 related to 1 is not there, 2 related to 2 is not there, and so on. Not symmetric also. You can see that why it is not symmetric. Because 1 related to 2 is there, but 2 is not related to 1. 2, 1 should be there in the relation, but here it is not there. So this is one example. You can find number of such examples. This is one illustration for you. Third, fourth, and fifth. Try to give such relations yourselves.